Welcome to our final video. So in this video, we will focus on CL04, which is modeling the outside environment by using the Gibbs function to find the chemical exergy and reviewing the simple gases. So to find the exact chemical exergy number, we must first agree on a standard model for the outside world, which is what we call our reference environment. So we model our standard outside environment at 298.15 K, which is at 25 degrees Celsius and 1 atm. We use fixed molar share for the common gases around us, which is nitrogen N2 for 75.67% and the oxygen O2 for 20.35% and water vapor H2O for 3.12% and also the carbon dioxide CO2 for 0.03%. So the table A26 show the two main variable, which is model 1 and model 2. In modern engineering design, we almost usually use the model 2 numbers. So what do we do if we have a field whose chemical exergy isn't listed in our standard appendix table? So we can calculate it by evaluating theoretical and reversibility reaction with basic components from our outside environment. By balancing our properties by using Gibbs function to keep the math easy, we will get our master formula, which is this very long formula. So this long formula can be think of two distinct bits. So first half is the change in Gibbs function value for the reaction, which you can pull directly from the table A35. And the second half is a concentration adjustment log term. This log part usually adds only tiny bits to your answer, so it is quite small. And then let's check this formula by finding the chemical exergy of methane gas, which is CH4 at 25 degrees Celsius and 1 atm. So for methane, our few numbers are A equal to 1, B equal to 4, and C equal to 0. By plugging this into our formula along with our Gibbs value from A25 and environment percentage from the table, it will give a calculated result of 830,000 kilojoule per kilomole. If you compare this with the published standard value in the table 826, which is 831,850 kilojoule per kilomole, you will see they are almost identical. So this shows that our basic equation work beautifully and it will give a highly accurate result. Then to finish up, let's look at a unique case, which is carbon dioxide CO2 gas at 25 degrees Celsius and 1 atm. Because CO2 is fully burned, it cannot catch fire or react anymore. For this gas, our numbers are A equal to 1, B equal to 0, and C equal to 2. When you plug this into the master equation, the chemical reaction terms cancel out to 0, leaving just the expansion log part, which is E power of minus CH equal to long equation. Then this simply measure the work you could get if you expanded pure CO2 through a small turbine down to its very low partial pressure in our regular outside air. This gives us a small but real value of 20,108 kilojoule per kilomole, which is a close match to the table value of 19,870 kilojoule per kilomole. That's complete our expanded 5 video masterclass series for chapter 13. So that's all from me. Thank you.